So the focus now is not just the big idea, it's all error sources of the GPS measurement. I pointed out already your clock have a bias. And we always say, hey, let the t equal to time. This universal time is a concept. Nobody own any universal time. The time may be Greenwich observation station have a little bit more accurate time. Other than this, every clock has a bias. So there's no such a universal time. Second, you look at all the noises. You know, any instrument has a measurement error. And then you look at the weather. You have so-called the ionospherical delay and the tropospherical delay. That's because the electromagnetic field in the clouds. Well, you have multipath. I said the multipath before. If you have a building here, let's say this is the street you're driving through, and the satellite signal could be bounced from the building to the receiver. That's called the multipathes. It's a big research field still. But anyway, this is just to tell you a whole list of error source we have to consider as the real technology. I would suggest you read chapter 4 of the reference 2. That's a very easy reading compared to the math. Now let's look at the ground stations. In order to make the GPS position be predictable, be always in the predetermined orbits and the position. And the states have more than 10 of these ground stations. There's one master station at Colorado Springs. And then there's observation stations, monitor stations across the whole Earth. You have to be even spread it because the satellites spin on the Earth twice. And we have antennas and everything else. So with this hundreds or billions of dollars of investment, we can pretty confident about the GPS clock itself. It's not 100% accurate, but it's fairly accurate. And we can be trust the position of a GPS satellites. You should know the time and then the position of the satellites. So that's known. The position of the satellite here, you can look at this ABC here. So those A1, A2, A3, B1, B2, B3, C1, C2, C3 is known because their position is monitored by those ground stations. And then the ground station will adjust the position if it's a little bit deviated from the pre-designed position at a particular time. We call it a calibration. Anyway, so what I have to consider is the clock of the receiver, because we probably pay $100 for a GPS receiver, actually now cheaper. You cannot expect high quality, like a scientific quality of the clock, which the accuracy goes down below milliseconds. So you have to also include the time drift, because in a short time you can have the accurate clock, but let's say your battery started to run out, your clock started to slow down. And the cumulating effect of the drift time, that's the big problem for all your watch, clocks, anything. So in summary, the time drift of the use clock must be a variable. In another word, that is unknown. You can read your watch, but you really don't know how much error you have. You need to put that into a variable. We call it B. B stands for bias of the clock. Well, once you keep that in mind, now how many variables we should have for the positioning? Your positions X, Y, Z, and you add another bias B, then you have at least 4. We actually have 4 variables. If you have 4 variables, you need 4 equations, right? That's algebra. And then the minimum number of satellites you need is 4. So you need 4 satellites to use your GPS receiver. Now, let's go to the GPS model, the real mathematics equations. Well, now we have a few things. This is the pseudo range measurement. That pseudo range measurement comes from the difference between your clock and the clock of the satellites. Multiply the speed of light. So that's the measured distance. And this is the supposed real distance. If you know your own position, that distance comes from the calculation between your position and the satellite position. Now, based on this formula. And this X is your position, Y, Z, your position. XI, YI, ZI is the ith satellite position. This I is simply tell you which satellite you're talking about. If I equal 1 is the first satellite, I equal 4, the fourth satellite. Okay, this I just distinguish the satellite. So that distance formula is the real distance, which you do not know, by the way, from yourself to the satellite. B, we talked about, is the bias. That assume they are universal across all satellites because your clock is wrong. So how much your clock is wrong make how much bias. So this B is a constant to the receiver, have no difference from different satellites. Well, the last one, we already know that. In all minimization, we got this arrow, we call it random arrow, or we call it white noise. Anyway, so how many of equations like this? Let's say we have 4 satellites, then we have 4 of those equations. If we have 6 satellites, then we have 6 of these equations. That's the starting point, the measurement model. Well, next, you remember, we looked at this example in the last lesson. We need to linearize the distance formula. So how do we do it? And the distance formula have a square root, like x minus a squared plus y minus b squared plus z minus c squared. To linearize, we take the partial derivative, and you get the gradient. We did that before. And then, look at this formula one more time. Now, this little delta stands for change. in reality, we keep improving our estimate. So this delta rho I means the change from last measurement to this measurement. So you look at the difference of the measurements from this round to the previous round. And then this x0 is the position in last cycle, last time step. And then this is the old distance. Now your position delta x is this change of x, change of little y, change of z of your own position. So it's the user position change. So overall, this minus this is the old distance and the new distance based on the prediction. Why based on prediction? Because my x, y, z are prediction. I have no clue where I am, really. Keep that in mind. So that comes from the prediction model. So the measurement change equal to prediction change plus the bias change plus white noise. So now we can linearize this change, which is the gradient. And we did the gradient last time. You remember we got the geometric matrix from this gradient. So as a first order Taylor series, we approximate the change of distance by the gradient, which is the differential. You understand that? That's the same idea as we use this tangent line, that distance on the tangent line to approximate the distance change on the curve. That's the same idea. So the left hand is the distance as a square root function, and the right hand is the gradient times this linear function, delta x. I said delta x is right here. And add another variable for the bias change. You get this relationship. This equal that to write it explicitly. So no surprise, you got this matrix. Last time we call it satellite geometric matrix. Why is a satellite geometric matrix? Because each of this row here is the directional cosine vector. Just point from the satellite to the user. So here's the satellite, here's the user. That's the unit vector here, from the satellite to the user. Why I needed to have this one? Because I have this little b. You remember in the equation, we always add this b. Then 1 times b, you get the b. So the geometric always add this 1, and then you get a b.